Okay, so maybe we will get started. Let me just remind you of the very last thing that we did yesterday. So, this concerns the truncations, the eigenvalues of a truncation. So, if I have finite dimensional product space, T is self adjoint, then we have its eigenvalues. So, there are n of them, they are all real numbers in general. And what we defined was this notion of truncation, sometimes called compression, which is you somehow want to restrict T to a subspace W, but restrict in a certain sense. T may not leave W invariant. So, what you do is you define a new operator from V to V as follows. It first projects, so it is a composition of three things. So, you first project V to W, so that you kill W perp and you do not do anything to W. Then you add T on W. When you do that, the answer will not be in W anymore, it will go outside W, and then you project again to bring the answer back inside W. Okay. So, I mean I will call it V to V there. So, the answer is finally in W. Okay. So, I could also make this a V, but the image of P will land inside W in the intermediate steps. So, here is V, the answer will lie inside W. You apply T, the answer will go back into V. You apply P again, the answer will come back into W. Okay. So, that operation here, in a sense what it does is it takes things in W and maps it to something again in W, things which are in W perp it kills, right. And we said this is really the analog of doing the following at the matrix level. If you write a matrix of T with respect to a basis in which the first few basis elements come from W and the remaining basis elements come from W perp, then the idea is you write the matrix of T, you will get something in all four parts when you think of it as a block matrix, and this compression matrix PTP with respect to the same basis is just the same guy as above, but in which the other three components have become 0. So, this corresponds to doing things like taking a principal submatrix of a matrix and so on. Okay. Except the beauty of this construction is that it works for an arbitrary subspace W, right. I do not need, it is not a matrix, when you do things with matrices you are always thinking about that God given basis and trying to restrict to a subset of that basis and so on. Here it is not like that. I can take any subspace of V that I care about, and PTP somehow exactly captures the idea of what it means to truncate T to W. Now, when you do this truncation, yeah, question?
Excuse me, sir.
Yeah.
So, since there are four blocks,
Huh.
2 corresponding to W and 2 corresponding to W perp.
Yeah.
So, can we think that either of both of W can be used? Like we are using first block here,
Huh.
but second block can also be used.
Second block meaning you are looking for a matrix which will finally give me this, you mean? Only this will survive and the other three?
No,
Huh?
left side. Second row, left side.
This one alone.
Yes.
You want to make this 0. Is that what you mean?
Yes, sir. Is it possible?
Yeah, sure. I mean, you just have to manufacture an appropriate operator, right? So, to do what, if this is what you want to do, you would first want to project along P, then apply T, and then keep only the part that goes to to W perp. So, you apply I minus P instead of P. So, if you do P first, then T, then I minus P, then what it will do is it will just retain this portion alone and give you 0 everywhere else, because I minus P, if you remember, is the projection onto W perp.
Yes.
So, you could do pretty much what you want. You can get any of the four components by appropriately changing I minus P and P on the two sides. Okay. But this operator will have the property that it will map V, it will map W to W perp in some sense, right. It takes things in W and it sends them to some elements of W perp. So,
Yes.
but instead we are looking at operators on a subspace, things which will map W to W again. Is that okay?
Thank you, sir.
Yeah. Okay. So this compression has or truncation has the following property that we mentioned last time, that its eigenvalues. So firstly, PTP continues to be self adjoint. But then each of them is self adjoint, so it is PTP again, and the nice property here is that the eigenvalues, so they are all real numbers again. So if you call them mu1, mu2, mu k, right, where k is the dimension of W, then these mu i's are less than or equal to the corresponding lambda i's. So lambda i's are the eigenvalues of t. So this is for I equals 1 to k. Right, lambda I, of course, there are more eigenvalues. Okay, somebody should mute. Okay, so I take lambda 1, lambda k, and there are of course a few more, lambda k plus 1 through lambda n. So this this inequality only concerns the first k of them, right, mu less than equal to lambda n. Okay, now this is going to be important for what I am going to say. In particular, this means that the trace of this operator, so if you look at PTP, the trace just means it is the, see what is trace of this operator going to be? It is just, you know, what are its eigenvalues if you think about it. See, PTP is an operator from it's an operator from V to V. So when I really say eigenvalues of PTP are these, it's not quite correct. There are a bunch of zeros if you remember, right. See what is the matrix, is something there and then there are zeros everywhere else, right. So these extra dimensions all map to 0. You would sign in. Inequality will be what?
Lambda I less than or equal to mu I, because PTP is a sum matrix of the matrix T. So by Cauchy interlacing theorem, the eigenvalues of PTP lies between the eigenvalues of T.
Correct. So lambda 1 is bigger than or equal to mu 1, for example, right? No? Lambda 1 is bigger than or equal to mu 1, lambda 2 is bigger than or equal to mu 2, and so on.
Mu1 lies between lambda 1 to lambda 2.
Yes, but I am not using the other inequality. I am only saying lambda 1 is bigger than or equal to mu 1. That's all you are right. Mu 1 is also greater than or equal to lambda 2. I also know that by Cauchy interlacing. But I am not using that. Yes, correct. I am only using half of the interlacing. Correct. Okay, so I mean this is all we need. So I am not using the full power of this Cauchy interlacing. So I mean I did not prove this statement, but this half is actually not so hard to prove. You can just prove it by using that supremum condition, right, because there is this geometrical definition of what the eigenvalues are, and if you use them you can actually prove term by term that min of max is less than or equal to the corresponding min of max. Okay, interlacing requires a little bit more work, but for me the fact that I want to really use this trace of PTP is in fact less than or equal to trace of T. See, this is easy to see if you just restrict it to some submatrix, right, because all I am doing trace is sum of diagonal values. I can just say it is this trace, and then I mean it is not so obvious actually, come to think of it, because there could be negative values in the diagonal of T. So I can't conclude just by saying okay I only taken part of the matrix, so this trace is less than or equal to the full trace, because the extra trace bits may have had negative numbers, right. It's I only know that the eigenvalues totally have this property. So okay, good. So you can't even deduce it from there. Fine so far. Question?
Eigenvalues of T can be negative.
Eigenvalues of T can be negative, yes.
So how mu k greater equal to 0 means maybe 0 is less greater equal to
Sorry. I should not have said greater. You are absolutely right. Yes. Mu1, mu2, mu k are the eigenvalues, and the extra eigenvalues are all zeros. Absolutely. And a bunch of zeros. N minus k. Thank you. right. So, that corresponds to this bit. So, when you do PTP, what it is doing is W perp is being killed off. So, those will all give you 0 eigenvalues, those mean W perp, that dimension number of 0 eigenvalues.
Could you explain why trace of PTP is less than or equal to trace of?
Right, because what is trace? Trace is the sum of the eigenvalues, right. What are the eigenvalues of PTP? They are what I am calling mu1, mu2, mu k.
It's up to k you have to find, sir, but some other eigenvalues that t is negative will be there, means
I see what you mean. Okay, great. Let me not say that. Yes, you are absolutely right, correct. So, I have a certain application in mind. So, t, I am looking at the case when t is positive eigenvalues. Yeah, okay. So far we are good. This is all I can say in general. Thank you very much. Okay, so let's. I mean, when I apply it finally, all eigenvalues will be positive. Okay, we will do that. Okay, so let's now go to this issue of what's called the best approximation or least squares best approximation. So, what is least squares best approximation? It's the following problem. Okay, so let me state the problem. So, it says suppose I have a finite dimensional linear product space and I have a bunch of points. I have x1, x2, xm, let us say, okay, some m distinct points in V. Now, what we want to do is the following: given, let me also fix k greater than or equal to 1, we want to find a subspace of dimension k, find a subspace W of V of dimension k such that, with what property? Such that it is the sum of the squares of the distances to these points is the minimum possible. So, here is the picture in mind. I want a subspace. So, let us say imagine the action is taking place in let us do R2 first. So, I have R2 and I have a bunch of points. The idea is to find a line through the origin. So, let us now say I want k equals 1. So, k is the dimension of the subspace I am fixing. So, my problem statement is the following: find a subspace of dimension 1 in R2. So, dimension 1 is just a line. So, I want to find a line such that the sum of the squares of the distances to these points is the minimum possible. Okay. So, I have got a bunch of points and I can compute the, when I say distance I mean the perpendicular distance. So, I have got these distances to these points. I want to minimize the sum of the squares of the distances. Likewise, if I am, let us say, in R3 and if k is 2, so here's R3 and suppose k is 2. So, then the question asks find a plane through the origin, right. That is a subspace of dimension 2 such that the distance, sum of the squares of the distances to a given set of points is minimum. And here again distance just means you find this perpendicular distance to the plane. Okay. So, let me complete my statement. I only wrote half of it. Find a subspace of dimension k such that what should happen? Such that the sum of the squares of the distances. So, what is square of distance? That is norm. So, I want norm square of. So, how do I capture this distance here? What is this perpendicular distance? How do I write it?
Projection form.
Xi minus projection of xi, right. So, these foots of the projections, I mean these foots of these perpendiculars are my projections. So, this point is xi, this fellow is my projection xi. So, I want to minimize this, is the minimum possible, okay, where P denotes just the projection onto W, okay, an orthogonal projection. Fine. So, this is the standard classic sort of least squares approximation problem. Here the extra condition we are placing is that it should be a subspace. In other words, it should be, for example, a line through the origin or a plane through the origin and so on. More general least squares things would say, okay, find even any line, not necessarily through the origin, right, something which is not, with some intercept is also okay, but in a sense these two problems are equivalent. You can reduce that to this. So we'll talk about that. So let's solve this problem first. Okay, so let's do the case k equals 1 first. So we'll see what this has got to do with all our earlier discussion. So let's first do the case of k equals 1. So what does that mean? I've got some vector space V, I've got a bunch of points. So for example, I'm in R3 and I want to find a line. Still a line through the origin which minimizes these distances to these various points. Okay, now let's make a simplification. So observe that norm of xi minus projection of xi square. So this xi minus projection xi is really this, right? So I have xi, this bottom is projection xi, but these three guys actually belong to this right angle triangle, no? So I have projection xi, I have x minus projection xi, and I have xi itself, right? So these two legs, projection xi and x minus projection xi, are perpendicular to each other. So that's what orthogonal projection meant. So in a sense we have got, if you just plug in the definition here, you will get the Pythagoras theorem, right? This is just from the property of inner product that x minus pxi is perpendicular to px. Is all right? Minus is correct, because norm xi, that fellow is the hypotenuse, right? Xi is the hypotenuse, x minus pxi and pxi are the two sides. Okay, so therefore the minimization problem I can rephrase it as follows. I want to minimize this sum, right? So I put sum on all sides. Now remember, this first term is fixed anyway, right? Summation norm xi square, this is some constant, because it is just the given points, that is all. What I am trying to vary is my projection P, I am trying to vary my subspace. So the second guy, I need to, if I have to minimize the left hand side, I have to maximize the second term. That is basically what I have to do, correct. So it is now a maximization problem of the sum of the squares of the norms of the projections. Okay, so let us write that out. So we now know enough to say what that quantity is, sum of the squares, the norms of the projections, there will be m points, some vector space. So this guy is, so if you remember what is the projection, so how should we state what the projection is? So remember here my subspace W I am choosing to be a one dimensional subspace, right? I am doing the case k equal to 1 first, okay. So I am trying to solve the problem for k equals 1, which means W is some one dimensional subspace. So let me do the following, let me think of it as being the span of some norm 1 vector, okay. So let us pick a vector V in W of norm 1. So I will think of W as the span of this vector, okay. Now why am I doing that? Because I can write a projection. So remember, to write a projection I need an orthonormal basis for my subspace, right. This vector here is my orthonormal basis because it is one dimensional. So the formula for the projection, if you remember, is just x inner product orthonormal basis into orthonormal basis. Here there is only one basis vector, so that is all it is. And the norm square is just the fellow in front. So this norm square is just modulus of xi v ka square. It's all right, because V has norm 1. Okay, so I'm basically trying to maximize this guy, right? I want to maximize by varying V. Okay, what am I allowed to vary? I am allowed to vary V, and V is some vector of norm 1 in my vector space, right? Okay, so let us do the following. Let us think of this as the following map. So this quantity here, so I want to create, see I am basically squaring m numbers, right. For example, imagine I am in the real world, or the field of real numbers. This is basically I have m numbers, x1 inner product v, x2 inner product v, and so on, and it is the sum of the squares of those numbers, right. So what I will do is I will just think of that collection of numbers as a vector. Okay. So what do we mean by that? Let us just state this. So let us define an operator T from V to, so there are m numbers that I want. So let me just assume V is a real vector space. Okay, you can do the same thing over the complex numbers if you want. So what is my map? It is just going to take each vector V to this m tuple. Okay, I am going to write down these m numbers. Is all right. So what I have done is
XM.
xm, thank you. So I am just writing out these m inner products.
Hello, sir.
Yep.
The norm of xi minus pxi square is equal to norm of xi square minus norm of pxi square, which should be plus, I guess.
No, it is minus, because see this xi, this guy is the hypotenuse, xi is the hypotenuse, and xi minus pxi is this vertical segment, right. This fellow is xi minus pxi, this side is pxi, and the hypotenuse is actually your xi. So I have just used Pythagoras theorem with hypotenuse square minus one of the side squares is equal to the other side square. So it is minus. Is all right?
Okay, sir. Okay.
Yeah.
Thank you, sir.
Yeah. Okay. So now I have got this this vector. Essentially, to each vector v in V, I am associating an m tuple of numbers, which is inner products of the given points with V. Now what is my so what is it that I am now wanting to maximize? This quantity is just norm of TV cos square, right. So my problem becomes the following. I am converting it one more step of reduction. I have now restated my problem as follows: find V of norm 1 such that this norm of TV cos square, okay, this norm is in what space? It is in the space Rm. So let me write that also. See, I have created the space Rm out of nowhere, right. This did not somehow naturally figure in my original problem. I only had my vector space V to start with, but inside V I had m points. Now using those m points, I am now giving you a map from V to Rm, which is basically take any point of V and you take its inner product with the m given points. Okay, that generates m numbers, and that is my element of Rm. So if I think of it like this, then the given quantity here is just the sum of the squares of these numbers. So it is just norm of TV cos square. Is all right so far? Okay, so I now want to maximize. I want to find V such that this guy is maximum. Okay, now let us do one more reduction. So TV square. So remember, this is in the space Rm. This is inner product of TV with itself in Rm. Okay, now what can I do with this? T, remember, is a map from V to Rm. Anything you can think of? So T is a map like this. So there is a map called T star, right, which goes in the opposite direction. Okay, so there is a map T star, the adjoint operator. So remember, this is the benefit of having worked or defined adjoints in the general setting of random two vector spaces V and W. That is the correct way to think about adjoints, though in many applications we are usually only looking at V to V, but the general case comes up in many places. So here, for example, TV, what I am going to do is I am going to push this T to the other side. Okay, I am going to use the property of adjoints. So, when I push the T to the other side, it becomes T star TV comma V, but now where is the inner product being taken? It is in V or RM? Okay, it's in V. So, remember this, see that adjoint is this very subtle object, right? It satisfies an inner product identity equation. That equation, if you remember, one side of the, if it is a map from V to W, one side involves inner product in V, the other side involves inner product in W. So, it converts this inner product to the other inner product in the other space. So, this is what it is. Norm TV square is just T star TV comma V, but then the inner product is being taken in the vector space V. Okay. So, this fake vector space RM that we created is now out of the picture, and now this should look familiar. Yeah, question?
So, can we say that it basically preserves the norm?
What do you mean by it preserves the norm? No, it does not preserve the norm. See, preserving norm is like saying TV ka inner product is equal to VV ka inner product.
Yes.
Only then it says it preserves the norm. Here it is not preserving the norm, I am just using the property of the adjoint, that is all.
But norm is equivalent because the 5-dimensional.
No, norms are equivalent is a different matter. Equivalent says you can find a bijective linear map isomorphism from one to the other, which will convert this norm to that norm and so on, right? But that is not.
Because V dimension is same, so RM also dimension is same dimension.
No, say that again. No, V is not of dimension M. No, V I did not assume dimension M. In fact, V is going to be different dimension in general. See, I have taken, for example, here, no, V is R2. See, in R2 I can take 100 points. If I take 100 points in R2, the map I created is a map from R2 to R100. See, this is left side is R2, right side is R100. So, that is why I say that this vector space is sort of a fake vector space, the RM that I am creating, because its dimension is the number of points that I was given in my 2-dimensional space, right. So, I create this maybe very large dimensional, in application that is what it will be, there will be some, you have 1 million points, it is R power 1 million, right. But in a sense we want to get rid of that guy from the analysis. So, it comes up here, but then it will disappear in the next step. So, what we have done here is use the property of adjoint to convert the action back into the given space V, right. So, in V if I am given 1 million points, it is still alright, I am only computing now something happening in V at some level. Okay, I mean this is not a very serious remark. Okay. So, now let us see what our maximization problem was. It said I need to find a vector of norm 1 which maximizes this quantity, okay, which maximizes this guy, right. So, this should look very familiar, a vector of norm 1 which maximizes some operator V comma V. It is the largest eigenvalue, right. Remember, this was a geometrical definition of the eigenvalue, of the largest eigenvalue. But before we do that, we should just ensure that this fellow T star T that we are looking at is a self adjoint operator. Okay. So, T star T is what is it? It is an operator from V back to V, right. So, I first do T, then I do T star. So, that is my operator. So, T star T is firstly an operator on V, and observe its star is just, now remember AB whole star is A star B star. So, sorry, B star A star. So, this is just going to be T star T. So, it is actually self adjoint, and the maximization problem we know therefore that the maximum value as V ranges over the unit sphere of this quantity is just the largest eigenvalue of this guy, and further where is the maximum attained, and max is attained on the corresponding eigenvector, right, when V is equal to the corresponding eigenvector V1. Okay, we will ensure the eigenvector is normalized. So, you take the corresponding normalized eigenvector E1. Okay, which is fine so far. So, we have actually at some level solved the best square least whatever best approximation by a one dimensional subspace problem. If you are given m points and you want to find a one dimensional subspace which minimizes the sum of the distances squares, the answer seems to be the following. You create this operator called T from your given vector space to the vector space R power number of points, and you take T star T, that is a self adjoint operator, and its largest eigenvector, I mean not largest eigenvector, its eigenvector corresponding to the largest eigenvalue, that is some vector, right. That one dimensional space is in fact going to be the guy which will minimize this sum of the squares of distances. Right. So, remarkable theorem at some level, because it just took the given data and it actually spit out an answer, I mean very explicit. Okay.
But the matrix dimension becomes too high to find the first eigenvalue.
No, matrix dimension, that is why I made this point that everything is taking place in V. See, in R2 I have 100 points, right. Then what is the size of this matrix T? So, so let us say V is R2 for example, and I have 100 points. So, this is R100, right. So, this matrix T is 100 cross 2, right. I agree. So, that the intermediate matrix you are creating is some huge monster, but T star is 2 cross 100, right. And what matters is actually only T star T, which will turn out to be a 2 cross 2 matrix. So, it is a 2 cross 2 matrix which arises by multiplying a 2 cross 1 million with a 1 million cross 2 matrix for example, right. But finally, it is only a 2 cross 2 object, and therefore, finding its largest eigenvalue is a tractable problem at some level, right. So, that is the beauty of the adjoint. So, I think at some level that is something very interesting which is happening here, that you convert this intermediate large vector space back into this, you know, the small dimensional thing into which you may have been working to begin with. Okay. Okay, so that is one guy. Let us now solve the general problem. Remember, we posed the same thing for k cross k. So, now I want to ask, okay, I will not assume it is a line, instead I will assume it is some k dimensional subspace, okay, and then let us try to do the same thing. So, let us pose the minimization problem once more, sum of the squares of the projection. So, general k, so let k be any number, one or more, we want W dimension k such that sum of the squares of the projections is maximum and P is the projection onto W. Now, how do we write the formula for the projection? Same sort of thing as before. We need to take an orthonormal basis, right. So, let V1, V2, Vk, there are only k elements, be an orthonormal basis. Be an orthonormal basis of W. Then the projection of any x looks like this, summation x Vi, Vi. X Vj, Vj, j goes from 1 to k. Okay. So, what is this? So, again what is norm of any Px square, therefore? It is okay. So, I have to use the same operator that I used before, right. So, I had my operator T. Let us recall what T was. T was this operator. Every vector goes to this m tuple of inner products. So, I am going to use the same operator T, but now I have to rewrite this in terms of T. So, what is this norm Px square? Sum of the squares of x Vj square, but I remember sorry, this is for given Px, I want to write sorry, let me back up one second. So, I have to interchange order of summation also. So, let's write what we want, sum of the squares of the Pxi's, I goes from 1 to m. So, I will rewrite it as follows. So, this is actually sum I equals 1 to m, j equals 1 to k of mod x Vj square, but I will interchange the order of the summations. I will think of xi, sorry, xi Vj is it okay so far? So, I am not doing anything too complicated, but just a lot of writing. So, I have just added up all the sum of the squares, but now I am fixing a j and I am adding up all the over the i's. So, that inner sum, that what does that mean in terms of my operator t? Sum of all the, now what was my operator t? To define t, I had to fix my second component as some vector, here I am fixing as Vj, and first I will take its inner product with all the xi's, right. So, that is all, that is what I am doing here. So, this is t Vj cos square, okay. So, it is the same thing as before. See, earlier it was just norm of TV square, right. Where did that go? If V is this, then I said, so then I said the summation xi square in the earlier case was just norm TV square. Here instead of one V, I have got many V's, that is all. I have got an orthonormal basis V1, V2, Vk. I have to sum over all of them, that is it. So, when I change my W to be in k dimensional space, the thing I am maximizing just changes like this, okay. So, let us write that out again. So, now my maximization problem becomes the following: maximize sum of t Vj square, okay, where what am I varying? V1, V2, Vk varies over all possible orthonormal sets. So, varies orthonormal subsets of V, right. I just choose different orthonormal sets, their span is my W, their span is really the k dimensional space I am looking at, okay. So, I have thrown W out of the equation, I am just thinking of taking my ambient space, picking k orthonormal vectors in it and just choosing it in all possible ways and calculating this quantity, okay. Now, this is the same computation as before. Tvj can now be written as T star T Vj, correct, again same as before. Now, let us stare at this a little bit. Now, what can we do? So, I still have the same sort of thing. Earlier I only had one term, so I am maximizing T star T Vv, that was maximum eigenvalue. So, I was done. Here I have n furrows, so I have to think a little bit more, okay. So, again this is still the operator I am going to look at. This is let us say let us call it something for the moment, my operator A, my self adjoint, it is a self adjoint operator. But now the thing I am computing is A Vj, right. So, A is a self adjoint operator, but somehow the quantity which is relevant is summation A Vj comma Vj. What is this quantity? Think in terms of matrices maybe.
First k eigenvalues of A.
It is equal to the first k eigenvalues. No, why?
Sum of first.
No, but Vi's are not eigenvectors. Remember, I have to vary it over all possible. For now, forget varying. Let us imagine I fix. Let me ask it like this. I fix V1, V2, Vj. forget the maximization problem. For the moment fix V1, V2, Vk. For a fixed guy, what does this quantity mean? Trace, absolutely, right. Why is it trace? Because see, A Vj bracket Vj is like what? If you think in terms of matrices, what is the first column of the matrix? It is just going to be, I will write A V1 as a linear combination of V1, V2, blah blah blah, right. And the first component is just A V1 V1, it is inner product of A V1 with V1. The second term is just the inner product of A V2 with V2, right. So, this guy is sort of like the trace, except trace means I should write with respect to a basis of the whole space. See, if V1, V2, Vn were a basis of the whole V, then this summation will exactly be the trace of A. But here I do not have all n, I do not have an orthonormal basis, I have only picked k orthonormal vectors from my whole set, right. They form basis of W, right. So, W is the span of V1, V2, Vk. So, therefore, what is it? If I only go this far and I do not look at the remaining, okay. So, essentially it is like a partial trace. I write out the matrix of A with respect to V1, V2, Vk and some extra orthonormal basis elements, and I forget the rest, I only add the first k fellows alone, okay. Let me say it like this, I put zeros in the other places and I only add these elements. Now I can think of it as a trace, right. I put zeros everywhere else and it is now the trace of this new operator, okay. So, we have seen this before. What operator is this? P, okay, but T is T star T in this case, okay. So, I find this again a rather fascinating fact at the end of the day, that we have converted this quantity. See, this quantity is the sum of the squares of the distances. So, if I pick, so let us summarize, the summary itself is worth remembering. So, it is saying if I give you a subspace W of V, k dimensional subspace, and I give you those n points x1, x2, xm in V, given all this data, the sum of the squares of the distances is trace of P, T star T, P. So, that is what we have managed to prove, right. Already a very remarkable statement, I feel, okay, where T is that particular operator. So, that operator is always there, it is always in play, okay. It is an operator from V to Rm, which takes every vector to, okay. But now we are in business again, we know what we can say about this trace. The trace is the sum of the eigenvalues of, so this guy is the truncation, right. So, I have my operator T star T and this P T star T is just its truncation. So, let us first write out the eigenvalues of T star T, it is lambda 1, lambda 2, lambda n. Its truncation will have some eigenvalues mu 1, mu 2, mu k, and the rest are zeros, and n minus k zeros, okay. Now, here is the additional fact that I have here, this guy is actually positive, all eigenvalues of T star T are positive. So, this is the thing I began with, but so this is the place where I this is the application I have in mind. So, T star T is self adjoint, but that is only half the story, it is also what is called positive semi definite. Its eigenvalues are in fact not just real numbers, they are non-negative real numbers, okay. And the proof is very easy, you just compute, if I have an eigenvalue of T star T, so I have got some eigenvector, my claim is that these eigenvalues are all positive, right. How do we compute, how do we check? We just take inner product with V on both sides. So, this is lambda times Vv. So, I can assume Vv is 1, that I have normalized my eigenvalue, the left hand side, as we have done many times, you push the t star back to the other side, it becomes norm t v square, and of course norm is always a non-negative number. So t star t is a very special kind of operator. It is not just positive, I mean it is not just self adjoint, it is actually positive semi definite, which is just another name for saying all the eigenvalues are non-negative real numbers. So I actually know that this guy has all all of them are non-zero, and therefore the trace, so this is the thing that we wanted to say back then, the trace of p t star dp is actually less than or equal to the trace of t star t. Okay. Why? If you remember the argument, let us go back to the very first page. So the argument that I made back then is eigenvalues of this compression looks like mu and mu 2 mu k, the eigenvalues of other guys are lambda 1 lambda 2 lambda k and some extra terms, but now all these extras are all non-negative, right. So now we know that the sum of the mu's is actually less than or equal to, so sum of the mu's less than or equal to sum of lambdas, but that is less than or equal to sum of all the lambdas, because the extra things you are adding are all only non-negatives, right. So this trace, the trace of the truncation is bounded above by the trace of the whole operator, that is the crux of the argument. Is this fine? So therefore we have shown that, let us go back here, this quantity is at most the trace of t star t, and so we know an upper bound already, that this distances are always bounded above by that guy, but this bound is actually attained. We can, if you correctly choose your subspace W, you can ensure that these two traces are equal, right. So what can we, sorry, that is not correct, you can figure out what that maximum value exactly is, right. So this is bounded above by, I mean trace of t star t is too big, right, that is not what I want to say, it is bounded above by the sum of the first k eigenvalues, that is the bound I want, right. Let me say something even better, this is, I claim this is bounded above by the sum of the first k eigenvalues, right. The full trace, sorry, that was complete nonsense, so I did not need the full trace. So my claim is that this trace of the truncation is bounded above by the sum of the first k eigenvalues of my operator t star t, right, and that is just my earlier statement that mu 1 is less than or equal to lambda 1, mu 2 less than or equal to lambda 2 and so on. So sum of the mu's is less than or equal to sum of the first k lambdas, that is it. Okay, I did not even need positivity for this. Okay, but now the question is, can you figure out how to make equality happen in this? How can we choose our k dimensional subspace so that equality happens, that it is exactly the, you just choose the eigenvectors corresponding to the first k eigenvalues, right. So if you choose exactly those eigenvectors, then what will happen? Why will you get exactly the sum? Because of that formula, right. So where is that formula? Trace of t star t vi, yeah. So let us go back here. This is the thing that you want. So now if you take your vj's in this formula to be exactly the first k eigenvectors, so let us do that. So further, how do you make, if we choose v1, v2, vk to be eigenvectors, and you sort of normalize it, orthonormal eigenvectors corresponding to the first k eigenvalues of t star t, then the sum of the squares of the norms t star t vi will exactly be lambda I ka sum, that is exactly the sum of the lambdas, because these guys are all normal. Okay. So in fact it is exactly the proof that we did for k equal to 1, means the analogous proof. How do you maximize? You choose the first k eigenvectors. Is all right? Okay, so again this solves that original problem that we posed in a rather spectacular manner, saying you take R2, you take 100 points in I mean not R2. So, if I take some Rn, for example, some ambient space, and I pick 1 million points in Rn, so I get this map to R 1 million, but among these 1 million points I want to know, what is a k dimensional subspace which minimizes the sum of the squares of the distances to these 1 million points. The solution is just you write out your t, you write out your t star, you form your operator t star t, that is now just an operator on your controlled space, only on your small n dimensional space, not on your 1 million dimension, and you write out its eigenvalues and eigenvectors and just take the first k eigenvectors and take their span. That is a k dimensional subspace which is guaranteed to minimize the sum of the square norms from those 1 million points to this guy. Okay. Okay, good. So this is the solution of the best square least square approximation, and let us reformulate this problem in a form in which it also appears. So this is sometimes, so let me sort of look at a reformulated version of this problem. So instead of taking an ambient space and giving you a collection of points, you can also ask stuff like this, given a matrix A, okay, let me say M cross N matrix with, let me put real numbers for now. So I want M cross N or N cross M, maybe N cross M. I take an N cross M matrix with real entries, find a matrix B in the same space of rank k such that the norm of A minus B is minimum. Okay, now what does norm mean? So now firstly, what is my vector space that I am talking about? I am looking at the vector space of matrices. Okay, the vector space of matrices has an inner product as well, right? So remember, it's trace of AB transpose or A transpose. So this was the inner product between matrices. So it's that inner product that we are talking about. In particular, it means norm of a vector A, norm square is just trace of AA transpose. So this is in a sense the standard inner product. If you imagine a matrix as being a collection of numbers, it's like R power nm. It's just some very large dimensional real space. I mean, it's R power nm dimensional space in which you just have arranged the entries in the form of a matrix rather than as one long string of as a vector. Okay, so you want to minimize you want to find a matrix of rank k whose distance to the given matrix A is a minimum, but the norm being the matrix norm, sometimes called the Frobenius norm on matrices. Okay, so let us see why these two problems are really the same. Okay, it turns out this is just another way of reformulating the least squares problem that I spoke about. So let's try to reduce this to the earlier problem. So what do I have? I'm given a matrix A. So n cross m, right? So there are m rows. So let me call each of the rows as something. First row I will call it as A1, second row as A2, and so on. So each row is a vector, and there are m rows. Right. So what is AI? AIs are all there are n rows. So then I should change to m cross n. Sorry, give me a second. So let me get my n and m right here.
So A transpose is R.
A I guess at some level it does not matter what I am calling n is n. Okay. So no, m cross n is better because I want it to be eventually a map from Rn to Rm, right. So let's change this to m cross n. So let's hope that that will set up the correct equivalence. So I mean at some level it does not matter, but let me just see if this works. M cross n. So I have m rows and each guy is a row vector of length Rn, of length n, right, row vector of size n. So it has got n components basically. So I can think of it as Rn if it is a except it is a row vector. Okay. So I have these m points. So I am now going to think of it as m points in Rn. That is really what my AIs are. Okay. Now the matrix B that I am looking for. So what is the matrix B? So how is that a subspace? So I am going to convert this to the earlier situation as follows. My ambient space is in Rn, and inside Rn I am giving you some m points, which are A1, A2, blah blah blah, Am. So that is my picture. Now what is my matrix B? So B is supposed to have rank k, right. So what am I looking for? I am essentially looking for a bunch of vectors B1, B2, Bm, okay, such that the span is a subspace of dimension k, right. So that is my k dimensional subspace. The B I am looking for, its row space, the span of its rows is supposed to be something of dimension k. So that is my W, and let us see how this Frobenius norm will exactly match up with what we want. So what is this norm of A minus B, right? If you remember the, let us say norm square, it is all the same thing. See what is this A minus B, I mean what is matrix norm? It is just normal standard norm in R power mn, like I said, right. So it is basically each entry of the first matrix minus the corresponding entry of the second matrix cos squared, right, Aij minus Bij squared over all i's and j's. That sum is what my matrix norm is. So observe, matrix norm squared of between A and B is essentially, I could equivalently write it as follows. Take the first row, think of it as an element of Rn, second row is also, I mean the row of B is also an element of Rn. I will just take their usual norm in Rn, and now I will only sum over the rows.
So,
Yep.
so we will not use the trace definition here for the standard norm.
The standard norm is exactly the trace. This trace is just another way of writing the standard norm. See this trace of AB transpose, if you see what it amounts to, it is just summation Aij Bij, where I and j run over whatever 1 to n, 1 to m. If you unravel the trace definition, it is exactly the standard norm.
Yes.
Yeah, but now I'm just rewriting it slightly differently. I'm taking standard norm, but I'm doing it row by row. I'm thinking of first row, instead of taking every entry Aij Bij is a entry by entry, instead I am saying I will take inner product of first row here with the first row there,
Okay.
second row here with the second row
Yes.
there, and so on. Just another way of saying the same thing.
Big.
Yeah. Okay, so norm square of A minus B is just the sum of the squares of these distances, and therefore what am I saying? I want to minimize this, right. So how do I minimize this? So let us say suppose the span is fixed, suppose I have fixed a W, okay. So I have fixed some k dimensional subspace. Now I am allowed to vary my Bi's as long as they span the same space, okay. So I vary Bi in that manner. Suppose I give you that minimization problem, fix my span of the Bi's to be W, and then tell me when will this be minimum, okay. So what is that problem? So that is like saying I fix a W, then I give you, let us say I give you only 2 points a1 a2. So, I have 2 points a1 a2. My goal is to find 2 points b1 b2 in the fixed span inside my space W, such that this square plus this square is minimum possible, right. So, how will I pick my b1 and b2? You have to take them to be the orthogonal projections, right. So, what you do is you it is clear what my b1 has to be. My b1 has to be the orthogonal projection of it has to be the orthogonal projection of a1 onto W. b2 has to be the orthogonal projection of a2 onto W. If I choose those as my b1 and b2, then this will minimize my norm of ai minus bi, right. So, to minimize is minimum exactly when bi equals the projection of ai. Okay, so, this is with for a fixed W and then try to vary bi in W, allow them to vary in all possible ways in W. Okay, so, when will this be minimum? Exactly when bi's are the orthogonal projections of the i's. Okay. Now, the thing you want to do is also vary W. So, I want to say okay, W can be any k dimensional subspace, right. So, now you also vary W, among all k dimensional subspaces. Then what does it mean? It is exactly the problem that we posed earlier, right, which is to say I want to minimize, therefore, what we are doing is to say minimize summation norm ai minus pai cos square over all possible w's, right. W of dimension k, okay, where p is projection, orthogonal projection. Okay, is this clear? So, these two problems, even though a priori they are stated differently, one is in terms of matrices, another is in terms of trying to find the subspace of best fit, least squares, best fit and so on. Finally, because of the way the norm is defined on the space of matrices, these two are really the same problem. Okay. So, sometimes you will see this as a what is called a low rank approximation. I have got a matrix some size 100 cross 100 and you want to find approximate it in the best possible way by a rank 10 matrix. That is equivalent to saying find, do what we just said, find a subspace of dimension 10 inside the appropriate dimensional space. And the solution to this problem, we know what to do, right. You form that particular operator T, you take T star T and you just take its first k eigenvalues, the top k eigenvalues and the top k eigenvectors. The span of the top k eigenvectors are going to be exactly the best fit, the subspace of best fit. Okay, so that's the So this business of trying to take the top k eigenvalues and vectors somehow comes up naturally when you try to formulate this kind of a least squares best fit problem. Now, so I guess Pranabendhu has talked about singular value decompositions and so on, at least in terms of its applications. So that is just another, so I don't know, did he talk about the definition, the theoretical part of what an SVD was? No? Okay, so let us just do it because it's we are right there. So what we have talked about is exactly what goes into SVD. This is more or less the same thing. Okay, so the singular value decomposition is really the following thing. I have got, so I will just state it for vector spaces in general. I have got a linear operator between two finite dimensional inner product spaces, but they are not necessarily of the same dimension. Okay, so finite dimensional inner product spaces VW of two different dimensions. Okay, now the point is when you have this, there are two natural operators to consider. Okay, and they happen to be exactly the sort of thing which we were doing right now, which is t t star and t star t. So, there is an operator t star t from V to V, and there is an operator t t star is from W to W. Okay. So, this is from Rn. So, let us just think of Rn for now, real numbers, Rn to Rn, the other guy is Rm to Rn. Okay. And we have already seen some properties of these guys, they are in fact both self adjoint and positive semi definite operators, right. So, we actually know something about these guys, they are self adjoint, and positive semi definite means the eigenvalues are non negative real numbers, right. So, it holds for both operators. Okay. Now, so let's make the following observation about these guys. I mean the sizes are different in general, right. So, t star, so t star t is going to be, if you think of matrices, it is n cross n from V to V, the other guy is m cross m, and so this fellow will have n eigenvalues, right. I mean the number of eigenvalues is n. This has m eigenvalues, but it turns out that the non-zero eigenvalues of both these operators are exactly the same. Okay. So, this is one of the first observations one makes when writing out what the singular value decomposition is. So, here is little proposition, it says that the non-zero eigenvalues and the multiplicities, okay, of the eigenvalues. So, multiplicity just means what is the, how many eigenvectors you get, or how many, what is the dimension of the eigenspace. The non-zero eigenvalues and multiplicities of t star t and t t star are the same. Eigenvalue itself is the same. So, let me write out the precise statement, i.e. lambda, okay, by this I mean non-negative real number, is an eigenvalue of t star t if and only if lambda is an eigenvalue of, sorry, I should say non-zero. So, it is already non-negative. So, what I mean is a strictly positive number lambda, it is an eigenvalue of t star t if and only if it is an eigenvalue of t t star. Okay. Further, the dimensions of the eigenspace, okay. So, this is from V to V, from W to W, the dimension of the lambda eigenspace of t star t is equal to the dimension of the lambda eigenspace of t t star. Okay. So, what are V lambda V W? Just mean you take all vectors in V on which t star t acts as, this is the lambda eigenspace, this comes from W, t t star, okay. So, these are the two eigenspaces. The claim is that you know that actually the dimensions of the eigenspaces themselves are the same. Okay. That is what we mean by the multiplicity of the eigenvalue being the same. So, if I have 10 linearly independent eigenvectors for the eigenvalue 1 in one case, you will have 10 linearly independent vectors with eigenvalue 1 in the other case also. Of course, this is not true for the zeros. I mean this cannot possibly be true, because one of them has n eigenvalues, the other fellow has m eigenvalues in general, right. All we are saying is that the non-zero eigenvalues correctly correspond, but the zeros will differ. One fellow will have fewer zero eigenvalues, the other guy may have more zero eigenvalues. So, that is the only difference you can have. Okay. So, let us prove this, because it's again more or less straightforward what maps set up the isomorphisms. So, remember there are maps t and t star between these spaces. The claim is that t maps V lambda to W lambda. And in fact, t star maps W lambda to V lambda. So, this is the correspondence. How do you map this eigenspace to that eigenspace? There is nothing to do, just apply T, it will take these eigenvectors to those eigenvectors, apply T star, you will come back. Okay. And so, that is going to be the map between the two. So, let us prove this. So, I have an eigenvector V. So, V is in V lambda, that means what? T star T acts as lambda V, right. Now, my claim is that if you apply T to it, it will become an eigenvector of T star. Okay. So, this is the known property. Now, my claim is that if I apply T on V, it becomes an eigenvector for the other operator for T star. So, let us check what you get if you do this. So, apply T star to TV. So, that is T star T, I can push that inside. T star T I know is lambda V. So, lambda comes out, it is lambda TV, right, which is exactly what I had to prove, that T star on TV is lambda TV. So, TV is an eigenvector for, so therefore, TV is actually an eigenvector for the eigenvalue lambda. Okay. Likewise, you can prove the converse, this is exactly the same proof that. So, therefore, I proved only one direction actually, I have shown T V lambda subset of V lambda, subset of W lambda. Likewise, you can prove the other direction, T star W lambda is subset of V lambda if you wish. So, T and T star are actually maps which send V lambda to W lambda and W lambda to V lambda. T will map this there, T star will map that here. Okay. But the claim is that these maps are actually isomorphisms, they are invertible maps between these two. Okay. In fact, they are more or less inverses of each other. What do you get if you compose one with the other? So, I go along T, come back along T star. Not quite the identity.
On the k dimension it will get.
Hmm?
On the k dimension.
No, what is K? There is no K here.
I mean the rank of the.
Oh no.
No. So, I am only acting it on V lambda, remember the lambda eigenspace. It will be lambda times identity, right, because just apply, you take a vector V in V lambda, you go along T, you come back along T star. So, what is T star TV? Well, V was a eigenvector for exactly this operator, no, for T star T only by definition. So, in fact, T star T is actually lambda times identity if you wish, it is lambda times identity on V lambda. Likewise, T star will be lambda times identity on W lambda, the other space. No, it is only lambda. See, because what is definition of V lambda? Go back to V lambda. It is T star T should act as lambda on it, right? It is the eigenvalue lambda for T star T, not for T. See, T eigenvalue of T does not even make sense, because it is a map from V to W. You cannot talk about eigenvalues and eigenvectors. It has to map back to the same space for you to be able to talk about eigenvalues and eigenvectors. So, what this means is, these two maps that we have constructed from V lambda to W lambda, they are actually, I mean their composition is lambda times identity, and why is that invertible? No, just this operator lambda times identity. Why is that an invertible operator on a given space? Lambda is non-zero, right? See, I have not used that assumption anywhere until this point. So, I only said non-zero eigenvalues correspond to each other. Until this point, everything I said will work for 0 also. So, the point is this is an isomorphism because lambda is not 0. So, of course, it is invertible. So, lambda is not 0, which means you basically what is the inverse of T? So, T star T is an invertible operator. In other words, you have the inverse, it is 1 by lambda T star. So, the inverse of T on this guy is just 1 by lambda T star. On each V lambda, it is a different guy, it is T star divided by lambda, where lambda is the corresponding non-zero eigenvalue. Okay. So, what we have basically proved is that this map, I mean these spaces V lambda and W lambda are of the same dimension, because there is a isomorphism between them, T and T is an isomorphism between these two spaces. So, they have the same dimension in particular. In particular, if V lambda is not 0, in other words, if lambda is an eigenvalue, then W lambda is also not 0, right. If lambda is an eigenvalue for T star, it is an eigenvalue for T star T also, because in particular dimensions are equal. Okay. So, this required non-zeroness, and like I said, the 0 eigenvalues are extra, right. Those will not match because the total ambient dimensions are different. So, where can the difference occur? Only in the 0 eigenvalues. Okay. So, this is the first observation, which is the starting point of this whole singular value decomposition business. So, the singular value decomposition can be thought of as just a clever choice of bases. So, when I give you any linear operator between two finite dimensional inner product spaces or vector spaces, inner product spaces, it is a clever choice of bases on both sides, so that it sort of simplifies the matrix of the form of the operator with respect to that. So, what should we choose? So, we already know something. Look at all the eigenspaces. So, V lambda 1, V lambda 2. So I know what are the eigenvalues, right. Look at all the non-zero eigenvalues. So, I have some k non-zero eigenvalues, and then there is a 0 eigenvalue. So, let me write it as V 0. Okay. So, these first k are, let us say lambda 1 through lambda k are the non-zero eigenvalues, and then there is a 0 eigenvalue, and these are the different eigenspaces, right. So, I have got this decomposition. So, what I will do is, for each V lambda I will pick an orthonormal basis. So, pick an orthonormal basis V1, V2, Vn, right. So, maybe I should call it, let us say Vk, and these are the extras, Vk plus 1, k plus 2, Kn, be an orthonormal basis of eigenvectors of T star T. Okay. So, this is an orthonormal basis of V consisting of eigenvectors of T star T. So, is this alright what we have done? Because we know something about T star T and T star, we are saying take an orthonormal basis of eigenvectors of T star T.
The multiplicity of lambda is always 1.
No, not necessary.
So, like you separated with the boundary over the.
Huh? What? Oh, separated with the bar means, no, V1 and V2 can both be in the same eigenspace. Is that what you mean?
Yes, sir. The dimension may not be k.
No. So, I will tell you what I mean by this bar. So, V1, V2, Vk are the eigenvectors corresponding to the non-zero eigenvalues. Oh, you are saying the same k. Yes, I understood. Sorry, absolutely. Yeah, let's change this to something. Yes, R. So, I have got some R, where R is the rank. Yeah, so good. R is the correct. So, I have got V1, V2, Vr. These are the eigenvalues, eigenvectors corresponding to the non-zero eigenvalues. And R plus 1 onwards to n are the eigenvectors corresponding to the 0 eigenvalue, right. This I can always do. Okay. So, this is going to be my preferred basis of V. So, we have found a nice basis of V. Now, what we will do is just use our, we want to now copy the exact same thing on the other side, okay, but with the roles of T and T star reversed, that is all. So, our objective is on the W side also you do the same thing, you look at T star, the other operator, and again take an orthonormal basis of T star, okay. First few will be corresponding non-zero eigenvalues, and then the last will be the 0 eigenvalues, but we will choose that in a certain fashion. How do we get the eigenvectors of T star from the eigenvectors of T? We just saw, right, how you go from one to the other. So, this is the map. If you take an eigenvector of T star T in V lambda, how do you manufacture eigenvectors on the other side? You just apply T to it, So, this applying t is the operation which will take eigenvectors on this side to eigenvectors on that side. So, let us do that. So, let us just apply t to this collection of eigenvectors we have constructed. So, now okay, let me write this again. So, V1, V2, Vr, then Vr plus 1 to Vn. So, this is all happening on the V side. Now, I apply t to each of these fellows, so that I will move, I will go to the W side. So, t V1 is what I will call U1, t V2 is U2 and so on, t Vr is Ur. Okay. So, if V1 has eigenvalue lambda 1, what is the eigenvalue corresponding to U1? It is also lambda 1, right. Remember, this is for t star t, that is for t t star, okay. There is this correspondence. So, observe that if Vi is in V some lambda, then it means Ui is in W lambda, okay. The eigenspace lambda for t star t, that is eigenspace lambda for t t star, okay. So, there is this constant tension between t t star and t star t here, okay. So, I formed these first R guys. So, this is something that happens if only for the non-zero eigenvalues. I can't do that for the next guy. If I apply t to this Vr plus 1, what will I get? You will get 0, because these are the eigenvectors for the 0 eigenvalue, right. So, t acting on these guys are all 0, these fellows are actually in the null space of t. So, I do not do that. Instead, what I have is I have got a bunch of eigenvectors for, so these fellows on the right hand side are all eigenvectors for, so these are the eigenvectors of t t star corresponding to the non-zero eigenvalues. Now, I just extend it to an orthonormal basis, that is all. I pick these fellows arbitrarily, Ur plus 1 to Un. You extend this to an orthonormal basis by also taking orthonormal basis for the 0 eigenvalue, that is all, of the 0 eigenspace. Of t t star, and 0 eigenspace is nothing but null space, okay. So, the and remember, these two things will not be the same. So, V U M, sorry, right. So, the crux of the argument is that the non-zero guys on both sides, you make them correspond exactly. You find an orthonormal base of t star t, you apply t to them, they will all convert into orthonormal basis for t t star, and the 0 space, the null spaces, there you are kind of free to do what you want. You pick a orthonormal basis of the null space on the left hand side, you pick a different orthonormal basis if you want for the null space on the right hand side, okay. And this basis that we have chosen on both sides, that is essentially the singular value decomposition. So, we write out those two bases. So, on the one hand we have this basis, so V is not a vector space here, this is the V is going to be a matrix now, I will put a slightly different symbol. So, V is now the matrix whose columns are V1, V2, Vn, and on the other hand I have got U, which is the matrix whose columns are U1, U2, Un, Um. So, if those are your two matrices, and if I had an operator to be, so all this is, so I am trying to rewrite my original thing in terms of matrices. So, T was given as from V to W, but instead if I thought of those as Rn and Rm, so if it was actually a matrix, so think of T as a matrix, okay, T is some matrix A, M cross N. So, thought of as a map from Rn to Rm, then what we have shown can be written like this. So, at least in this basis things simplify quite a bit. So, AV, so it is like saying if I apply T to each of the Vi's, then the answer will become ui's not quite times some multiple. Okay, so that those multiples are this matrix called sigma. Okay, I think I should have, I mean there is a normalization there. Okay, so sorry, let me just fix this alone. So ui are, I mean if I write ui's like this, the trouble with it is, see the vi's are all, I can pick them to be an orthonormal basis, but if I apply t to it, it may not be orthonormal anymore, right. So I may need to normalize it. So there is a normalization constant that I need. So I shouldn't take u's to be this, I should divide this by its norm. So that is something that is customarily done. I mean the basic idea is what we have already said. It's essentially a clever choice of basis, but having done it, you then, if you want a matrix form of that equation, you have to ensure everything is normalized so that you get orthogonal matrices and so on. So if I just normalize these ui's, then what happens is the following equation. So if I rewrite everything back in terms of matrices, it becomes something like this. My matrix A multiplied by my eigenvectors on the v side, AB, will be my eigenvectors on the u side multiplied by sigmas, where sigmas are the norms of those vectors. So sigma will turn out to be an m cross n diagonal matrix. I mean you can't quite call it a diagonal matrix, but this fellow is sort of the norm of TV1, norm of TV2 and so on. Okay, and at some point it will end, and then the rest of the matrix is all zeros. So there will be R of these guys. Okay, and this particular form is what is called the singular value decomposition. So you can push the V over to the other side, and since we had all orthonormal eigenvectors, it is an orthogonal matrix, its inverse is its own transpose, and A will have this form, okay, and that is your singular value decomposition. But at the heart of this whole thing is this clever choice of basis, that is about it. I mean if there is one thing that you want to remember about what singular value decomposition is, it is just picking a basis of t star t on the left hand side and a basis of t star on the other side. Non-zero eigenvectors end up corresponding, zero eigenvectors are different in number, so there you do whatever you want, but these two guys you make them correspond exactly, and the correspondence map is just a map T itself which takes these eigenvectors to those eigenvectors. So if you just set this up correctly and then rewrite everything in terms of matrices, it becomes this so called singular value decomposition. Okay, good. So almost time to stop, so I will stop here.